Hello, I'm Professor Tom Scott from the University of Bristol, and I'm really pleased to be able to present to you my presentation on uncrewed aerial systems for applications in environmental survey and monitoring. My team at the University of Bristol and in conjunction with the National Nuclear Laboratory have keen interests in UAV radiation mapping in all types of applications, from site surveys all the way through to mineral mapping and resource estimation. The key thing about environmental radiation mapping, which stands it aside from, for example, facility monitoring, is that typically the key mission requirements that you have are to cover large areas, and that's often either within a single sort of site boundary, so within the site boundary of a nuclear site, for example, a nuclear power station, or actually in an envelope which surrounds externally the site, extending out maybe 1, 2 or more kilometers. That could be routinely surveyed to understand the background radioactivity, the natural background radioactivity, but also in the event of a nuclear incident, it would be the same areas which would initially be encompassed by any surveys. So with these kinds of environmental survey, there's a requirement to be able to distinguish between the different types of naturally occurring radioactive materials. Principally, that's uranium-related decays from thorium-related decays from potassium-40, and it's also a requirement to be able to distinguish what is natural from what is man-made, so those anthropogenic radiation sources, but typically fission products is what we're talking about. And of course, at the same time, when recording the data, there's a requirement to be able to visualize and remotely store that data in real time, such that if the aircraft is lost, you haven't lost the data. The data is transmitted to a safe base station or through a cellular network, for example, to the cloud, so the data is safe even if the aircraft isn't. And there's also a requirement often to be able to capture and account for variations in terrain and topography, recognizing that not all nuclear facilities or surrounding areas are perfectly flat, but you've got different terrain features like mountains, for example, or you've got ponds or lakes or even rivers or the sea, in fact, where often that can be quite important to account for those variations. Just to give you 2 examples, at Fukushima, for example, there was a mapping exercise conducted both with helicopters and later drones, and often higher levels of radioactivity were misidentified quite simply because the radioactivity was in the trees, caught up in the sort of the leaves or the furs on the trees, and therefore a UAV or a helicopter flying over those trees was effectively closer to the source of radiation when it was on flat than when it was on flat open ground, and therefore it made it seem that the forests were much more radioactive. They weren't, in fact. It was just that the radiation source was closer to the detector. Conversely, we often use open bodies of water, but typically wide rivers or lakes, in order to calibrate radiation detectors during aerial surveys, because water is a very effective attenuator of radiation, and therefore by hovering at different altitudes over water, we can provide a correction for the radiation which is coming from outer space, as opposed to the radiation which is coming from the ground surface below the aircraft. So typically, radiation mapping from the air has always been conducted by manned aircraft. This is typically planes or it's helicopters, but the important thing is that there is a manned flight crew on board, and that those systems typically will fly for very long periods of time versus drone technology, and that's because they've got fuel on board, but you're talking many hours of flight time, and sometimes with the ability to refuel mid-air as well. And of course, because they can fly for a long time, it means that they can cover a large area of ground very quickly in a single mission, whereas with drone technologies, usually you have to cover large areas with multiple missions because the flight times simply aren't there yet. But there are some issues with manned aircraft, specifically not being allowed to fly over nuclear sites. That's mainly because if the helicopter or the aeroplane were to get into trouble and it was flying over a nuclear site, the possibility of an impact or a crash into a nuclear facility would be disastrous, and therefore typically the airspace over nuclear facilities is excluded for manned aircraft. and also the fact that due to the possibilities of collision with terrain features, that most civil aviation authorities will not allow manned aircraft to fly below 120 meters. Indeed, that height above ground up to 20 meters is considered the domain of drones and UAVs. There's also the issue with manned aircraft that they're restricted in terms of where they can sortie from. They're restricted to taking off and landing at airfields, and therefore if the airfield is quite a long way from the nuclear facility or the area that needs to be surveyed, then this is taking up a certain proportion of the flight time before the manned system is actually over the target area that it wants to map. And last of all is the issue of cost. To maintain manned aircraft, you need to incur the cost of paying for the ground crew, paying for the air crew, paying for the upkeep and maintenance of the aircraft, paying for its fueling, and also paying for the storage of all of that on an airfield site. So to have a manned capability for radiometric mapping comes with a significant cost. So you can only do this if you've got substantial resources, whereas drone technologies offers a potentially much cheaper, much more versatile solution. So when we consider fixed wing radiation mapping using, for example, a twin otter aeroplane, we typically have a methodology where the aeroplane is flying parallel lines in opposite directions, typically at an altitude, as I said, of about 120 meters, with a line spacing of about 200 meters, which sort of gives an on-the-ground sort of pixel resolution of about 150 meters sort of diameter for measurement points. And with the speed of the aircraft, we're talking a single radiometric measurement point every 60 meters or 1 second. And so what this typically means is, because the aircraft are having to fly higher, and they're also traveling quite fast, that both the sensitivity and the spatial resolution of the radiation map are quite crude, and that you must use large volume gamma detectors, which means they're quite heavy, and therefore you can only carry them in larger aircraft in order to record meaningful data. It's quite simply a matter of, with manned aircraft, you are limited by the inverse square law. But with drones, you can actually capitalize on the inverse square law. And what I mean by that is that whilst velocity of the aircraft is important, the greatest factor which impacts on spatial resolution and sensitivity for a radiation survey is actually the altitude at which you conduct the survey, with the idea that as low and as slow as possible will give you the best possible spatial resolution and sensitivity. Of course, when a gamma photon is traveling through the air, or a population of gamma photons is traveling through the air itself will attenuate the radiation as a function of distance. So, for example, the mean free path of your average gamma photon emitted from the Earth's surface is typically less than 75 meters. And so if you have an aeroplane that's flying at 120 meters, that means that most of the gamma photons have actually already been attenuated by the air before they even get to the aircraft and the detector that's on board of it. And you can think of, therefore, as the air, the atmosphere, actually providing or posing the role as a low energy filter for airborne gamma photon measurements. And what this actually means is that a manned aerial survey will not detect soft gammas which are emitted from the ground, because the air is blocking them from reaching the aircraft. So in concept, it is always better to fly lower and slower to maximize spatial resolution and sensitivity, and this is exactly what drone technology allows us to do. So before I go to examples of drone technologies, I just wanted to provide an example of a manned aircraft radiation survey, which is really quite a significant effort, and that was the Tellus Southwest project, which was funded by the UK government and run by predominantly the British Geological Survey and the British Antarctic Survey together. And it was a survey conducted in 2013 where the whole of the southwest peninsula of England was mapped using combined LiDAR and radiometric mapping surveys. And what that produced was a 3D digital elevation model of the whole of the southwest of England, and with it a radiometric survey which could show us areas of high radiation low radiation, and it could also distinguish between the different natural types of radiation, but as I've said before, thorium related, uranium related and potassium related, and that really nicely corresponded with the geology of the region, which is dominated by granitic bodies which are poking up through the surrounding sedimentary country rocks. But this shows a really substantially large area mapped for radiation. Relatively speaking, the resolution is quite crude, but it provides an example of where there are areas of interest that you could explore with drones going much slower and much lower to provide a much better quality of information. But it provides a very good regional survey, I think you'll agree. Now, it's really, really important to consider why in some cases you might use a drone instead of a human being on the ground. And that's often because there's a requirement to make sure that you have 100% area coverage for an environmental survey. Now, if you're a human being carrying a detector in a backpack, either collimated or just uncollimated, the sort of field of view that you would have for collecting nearby gammas emitted from the ground surface is relatively limited. And therefore, if you are walking over an area, for example, with a standard backpack mapper, then you will have spatial gaps in your data where you simply aren't sampling the surface of the ground. Now, the advantage of the drone is just by flying that little bit higher, and you know this is anywhere between sort of 2 and 10 meters, means that the sort of aperture, which is fixed for most radiation detectors, is covering that much larger area on the ground, that between successive measurement points you have some overlap in terms of the ground coverage, meaning that as you conduct your survey, you can guarantee that you have 100% area coverage, whereas you simply don't get that in on the ground manned surveys. So aerial surveying gives you that better coverage, but understanding that you still want to fly as low as possible to get the best sensitivity and spatial resolution. The other thing that you need to do with a radiation survey, especially in environmental systems, is you need to be able to account for the terrain, as I've previously said. If you can account for the terrain, and specifically if you can account for the distance from the radiation sensor on the drone to the land surface beneath, then you are able to calculate the dose on the ground, the radiation dose on the ground, which is typically the sort of international norm is to calculate it for 1 meter above the ground. Now, obviously, you're not going to fly your drone at 1 meter above the ground, so you need to collect the radiation data that you might record at, say, 10, 20 or 30 meters altitude, and to correct that back to a dose map 1 meter above the ground. And the way that that is typically always achieved is to use LiDAR, so laser ranging effectively. So either as a single point ranging LiDAR, which points and fires straight down from the underside of the drone to give a very precise millimeter accurate measurement of the height above ground that the drone is at for each individual measurement that it takes, or to go one step further and use 3D scanning LiDAR to create a 3-dimensional terrain model or a point cloud model, which you can then use in post-processing to do to assist with inversions and interpolations in order to get a much more accurate calculation of the dose. So what this means is that for environmental mapping, almost always you want to combine laser measurements with radiometric measurements, and by combining the two, the quality of the data you get and your ability to unlock dose calculations becomes possible. Another example of a manned aerial mapping exercise, which then was followed by a UAV or drone mapping exercise, is in the aftermath of the Fukushima disaster, where the first radiation maps of the contaminated area were actually conducted by Black Hawk helicopters carrying sodium iodide detectors launched from carriers in the Pacific, and they flew lots and lots of parallel flight lines over different regions to create a joined up radiation map that you can see on the left hand side. Now subsequently the same areas were studied in more detail. This is Sanada et al. In 2014 that used a large drone helicopter, but it was unmanned, to carry detectors at about 80 meters altitude or less in order to conduct a radiation survey which has because of the low altitude, had a much higher spatial resolution. And so if you can consider for a second figure B, which is the manned aerial survey immediately around the power plant, and then figure C, which is the UAV based survey of the same area immediately around the power plant, what we can see is that the UAV survey has more sensitivity and spatial resolution, which means it's able to delineate not just one large radiation plume coming away from the site, but in fact 4 separate plumes coming from the site. And this underlines the value of being able to do environmental surveys with drones rather than manned aircraft. You can think of them as being complementary, but also you can think of potentially drones eventually replacing any manned capability, because of course, do human beings really want to fly aircraft over nuclear incident sites where there's a chance that they might get very high exposure to radiation and then subsequently get sick? If we now move to the Chernobyl exclusion zone, where I've also done quite an amount of work with UAVs, initially the mapping of the Chernobyl exclusion zone was done with helicopters, not mapping in the air, but with helicopters flying from location to location, and ground-based measurements were taken to create a sort of point map of measurements, which were then crudely interpolated to create a distribution map of the radiation. But of course, today we can do that differently. Here's a short video to show fixed-wing radiation mapping of the Red Forest, which is the first time fixed-wing drone radiation mapping has ever been performed in the Ukraine. So just after midnight, 26th of April 1986, we had the Chernobyl explosion. And now, more than 30 years on, we have the safe confinement structure, but still a lot of legacy contamination in the surrounding exclusion zone, but most specifically the Red Forest area directly to the west of the power plant, which is one of the most radioactive places on the planet's surface. So we decided to use fixed wing drones in order to cover a large area to map the Red Forest. You can see it's a hand launch. This is a Skywalker Titan flying at less than 60 meters altitude for the duration of all the survey flights. And you can see those flight lines as a series of sort of parallel running race tracks. Now, takeoff and landing was not easy. So to take off, we had to hand launch. To land, we had to use a parachute landing. And you could see there just at the end that as it lands hard, the tail comes off the drone. So takeoff and landing was an issue, but it allowed us to cover large areas. And then subsequently, with interest areas, we could go in low and slow with multi-rotor drones to get a better picture of any hotspots that we located. But it certainly highlights the capability of using fixed wing drones for large area environmental mapping of radiation. I think you'll agree. So in this exercise, we could cover something like 20 square kilometers of the Red Forest and the surrounding area in just a couple of days using the fixed wing system. Initially, we found that we had too much detector volume on board for some of the multi-rotor surveys, and therefore directly over the red forest we were saturating our detectors and subsequently had to change them to a combination of large cesium iodide crystals for the lower activity areas and small CZT crystals for the high activity areas where we could go to very high count range, and therefore provide a much greater dosimeter range for mapping in these very, very sort of unique and special terrains where the radiation levels over the red forest are extremely, extremely high. We also found unexpected hotspots that nobody knew about, that whilst we'd found them with the fixed wing survey, we could then follow up with a multi-rotor survey to go in low and slow and get excellent spatial resolution and pinpoint on the ground where we needed to sample as well. So we learned a lot from that initial deployment to the red forest. Specifically, one of the biggest challenges was around takeoff and landing, which is the most risky part of any mission. We also found that there was a really beneficial use of the fixed wing drones to cover large areas quite quickly, accepting that the spatial resolution and sensitivity wasn't as good as with multi-rotors, but you could cover a large area, you could find points of interest, and for those points of interest you could then deploy multi-rotor drones low and slow in order to then get a better handle on exactly where the radioactivity was coming from. We also learned that you had to really, really carefully plan your survey paths. You had to account for terrain. You had to account for things like tree breaks in terms of the ground heating up and you get unexpected updrafts. So you had to make sure the drone was incredibly well programmed to fly autonomously over the terrain. So that's quite a lot of reconnaissance work with drones before the main deployments. And you also needed to have a protocol for contamination checking and then decontamination if there was any, as well as recovery of any vehicle. You needed to have a plan in case you had a drone that went down unexpectedly and you needed to go and get it. You needed to actually be able to make a call whether it was worth getting or not. And the other aspect was needing to take at all times in-field battery charging. Very important aspect, because if you only have one set of batteries, then that limits significantly how much ground you can cover. So if you have, for example, a generator or you have a large vehicle with an inverter, you can have a continuous recharging of battery sets, which allows you to have continual mission after mission capability, so you can fly all day. So the takeoff and landing was a very major issue for us. So one of the things that we did very quickly after our experiences in the Chernobyl exclusion zone is we started to search for and then adopted a vertical takeoff and landing fixed wing drone capability. That vertical takeoff and landing capability solves the problem of takeoff and landing, the risky part about it, so that you don't damage your aircraft. And so what we've just been field testing is the new Wingtra variant of the AARM system, which is a vertical takeoff and drone with integrated radiation mapping. But it gives you the same benefit as a fixed wing drone covering large areas. But you don't need to have a large open space, or you don't need to have a runway for takeoff and landing as you do for your standard fixed wing drone aircraft. We've done some testing recently at the South Terrace radiation anomaly in southwest England in Cornwall, where we have a legacy uranium mine where radium was processed, and we have quite a significant anomaly which is really very well known and publicized, in fact. You can see here in this inset map, this was the first radiation map recorded using drone by Martin et al. In 2015. And so we've recently gone back to this anomaly with the Wingtra system to remap it and to show how much more capable we are in terms of large area environmental survey. So we take the big orange flying wing with the onboard radiation mapping system, which is a cesium iodide and CZT detectors side by side. And we're able to, in the space of a day, over 5 flights, each of about 40 minutes, map 178 hectares of the anomaly site and the immediately surrounding area, with a view to trying to find other anomalies or other ore bodies which might run parallel to that which forms the South Terrace mine. So we conducted flights at 70 meters, and those flights were conducted in relatively rainy conditions with headwinds gusting to 25 kilometers an hour. Because of the power of the VTOL motors, it meant that very easily the Wingtra system could fly into quite a strong headwind without a problem, which again wouldn't be possible with a standard fixed wing drone, which wouldn't have the same power. Now, the red line is the flight maps originally conducted by Martin et al. In 2015, and you can see how we've covered a very much larger area in about something like a fifth of the time, but with a comparable sensitivity because of the system that we're using. If we think about taking this capability and adapting it to other applications outside of nuclear, then the obvious one is resources, specifically for mining. So here's an example of Batalic in Cornwall, where we've done a UAV-based radiation survey. You can see those parallel flight tracks to delineate not only spoil heaps on the cliff surface, but also outcrop of a mineral vein which runs up the cliff face as well. And so not only is environmental surveying useful for nuclear sites and the surrounding areas, it's also potentially very useful for resource prospecting, and that's everything from the obvious ones like uranium and thorium prospecting through to evaporites and phosphorites, gold deposits, especially the placer type ones where thorium and uranium are coincidents, rare earths, coal and hydrocarbons, lithium granite, which you would determine inversely in relation to a decrease in radiopotassium, and also looking for water seepages as well to understand where there are aquifer bodies in the subsurface. And of course, for existing mine sites or legacy mine sites, you can use this same technology to understand the environmental sort of legacy footprint of radioactive materials, just as we see here in this figure. And that helps us understand environmental impact, and that's often a regulatory or permitting requirement that we do that. And also determining inactive mining sites where you have norm contamination, or you have zones where you have more intense norm present in the minerals, so that you can manage those radioactive tailings more effectively. So in summary, consideration for large area environmental radiation mapping applications is that the combination of vertical takeoff and landing fixed wing drones to cover large areas, and then enabling multi-rotor drones to do small areas of interest in much more detail, is a very effective sort of combination of tools for the mapping application. And so there's a real opportunity now with these technologies to initially complement manned aircraft capability, but also to eventually replace it, is my feeling. So we can use this capability for nuclear site mapping, emergency response, and resource prospecting. So thank you very much for listening, and I'd be happy to answer your questions at the end.